Hello everyone, welcome to track 5. We have another presentation lined up for this technical session 4 on the theme Next Generation Plants and Assets. The third presenter of this session is Mr. Atif Jamil from Aligarh Muslim University. He is going to present on multi-class fault classification of rolling element bearing in machine learning environment. Over to you, sir.
Hello everyone, welcome to International Conference on Condition Monitoring on Agile and Sustainable Advances in Equipment Reliability through Condition Monitoring. This is Mohd Atif Jamil, research scholar from the Department of Mechanical Engineering, Aligarh Muslim University, India. Currently, I am also working as a guest faculty at University Polytechnic. Prior to that, I have also worked as assistant professor in a private engineering college for about 6 years. The title of my research paper is Multi-Class Fault Classification of Rolling Element Bearing in Machine Learning Environment. These are the contents of my presentation. I'll quickly move on to the introduction. Bearings are vital components of industrial rotating machinery, and about 70% of these bearings fall under the category of rolling element bearing. So it is quite necessary to establish or to develop some suitable condition monitoring techniques for bearing health monitoring so as to avoid breakdowns during operation. Bearing defects. The reasons behind bearing defects may be faulty installation, improper maintenance and handling practices, or surface fatigue. The bearing defects may be broadly classified as local defects, extended defects, or distributed defects. Local faults may be in the form of spalls, small pits and cracks. In the extended defects, the defect size is greater than that of the angular spacing between the rolling elements. And distributed defects may be in the form of off-size rolling elements, surface roughness, waviness and misaligned races, etc. The common techniques employed for condition monitoring of bearings are temperature monitoring, acoustic emission, sound pressure, stator current, oil monitoring and vibration monitoring. In this particular work, the ML techniques are implemented over vibration data. Vibration monitoring relies on time domain, frequency domain and time frequency domain features. Mean, standard deviation, skewness are some time domain features. Power bandwidth, peak values and peak frequencies come under the category of frequency domain features, and spectral entropy, spectral kurtosis and some higher order metrics are time frequency domain features. Artificial intelligence and machine learning in condition monitoring. Artificial intelligence is a procedure of making a computer to think intelligently similar to the human beings, and this is achieved by developing intelligent softwares and systems. Machine learning is a subset of AI and is a concept which allows the machine to learn from examples and experiences. It can be effectively applied to fault classification problems for bearing health monitoring. The machine learning techniques are categorized into 3 classes: the supervised learning techniques, unsupervised techniques and reinforcement learning techniques. In supervised techniques, the input data is properly labeled and it is suitable for classification and regression problems. Unsupervised learning, there is no labeled input data. The system or the model itself tries to identify the variation in the data and clusters them. So it is suitable for clustering and association analysis applications. The reinforcement learning is based on the interaction with the environment and it is suitable for robotic applications like automatic cars or self-moving cars, self-driving cars and high-end gaming, etc. CWRU bearing data source. CWRU stands for Case Western Reserve University. This university has a bearing data source where healthy and defective bearing data is collected at sampling rate of 12 kHz and 48 kHz for motor speeds varying from 1797 to 1720 RPM using accelerometers installed at motor housing. The test setup is shown in this figure. It has a motor at the left end, a dynamometer at the right end, and a torque transducer and encoder in between. Accelerometers are mounted at fan and bearing and the drive and bearing. Experimentation is done for inner race fault, ball fault, and outer race stationary faults located at 3 o'clock, 6 o'clock, and 12 o'clock angular positions with fault diameters ranging from 7 mils to 28 mils, where 1 mil equals 0.001 inches. Data is collected at sampling frequencies of 12 kHz and 48 kHz for motor speeds ranging from 1797 to 1720 RPM, and experimentation is carried out for inner race fault, ball fault and outer race stationary fault located at 3 o'clock, 6 o'clock and 12 o'clock angular position with fault diameters ranging from 7 mils to 28 mils, where 1 mil equals 0.001 inches. The data subset used in this particular work has a sample frequency of 12,000 Hz, approximate motor speed of 1772 rpm, fault size of 0.007 inches. 4 fault categories are considered, which are healthy, inner race fault, ball fault, and outer race fault, particularly located at 6 o'clock location. 10 samples from each fault classes are considered with a sample size of 6,000 observations each. Further, these 4 fault classes are assigned with numeric fault code of 1, 2, 3 and 4 respectively. The cross-validation approach in machine learning. Cross-validation is a method for assessment of prediction models by splitting the input data into a training set and a test set. In k-fault cross-validation, the original sample is randomly split into k equal size subsamples where k is an integer equal to or greater than 2. From these subsamples, a single subsample is retained as the validation data for the testing of model, and the remaining k-1 subsamples are used as training data. As you can see in this figure, this is the actual input data from which the subsample equal to k in size is retained for validation purpose, and the remaining k-1 subsamples are used for training the machine learning model. Similarly, in iteration second, the first subsample is used for the training purpose, whereas the second subsample, which is of course equal to k in size, it is used for the testing or the validation purpose, and remaining data is also used for the training purpose. Similarly, in the third iteration and ultimately in the kth iteration, the last subsample is retained for the validation purpose, and the remaining k-1 subsamples are used as training data. So the advantage of this particular method is that all the observations are used for both training as well as validation, and each observation is used for validation exactly once. Feature extraction and model training. MATLAB 2019A is used for the analysis, from which diagnostic feature designer app is used for feature extraction using a multifunctional graphical interface, and these features may be compared interactively to find out the best features that can distinguish between the data from different fault classes. And classification learner app is used for training of the machine learning models. The results are presented in the form of scatter plot and confusion matrix. In scatter plot, the selected features are identified as predictors, which may separate the fault classes well by plotting the different pairs on the scatter plot before training the classifiers. The features selected this way are clearance factor, crest factor, impulse factor, kurtosis, mean, signal to noise ratio, shape factor, and skewness in this particular case. The confusion matrix helps understanding how a particular classifier performed in each class, and the diagonal cells show where the true class matches with the predicted class. Results and discussion. The plot on the left shows the ensemble vibration data from 4 different classes, 1, 2, 3 and 4, and the plot on the right is the corresponding power spectrum for these 4 classes. These are the scatter plot and confusion matrix for a particular machine learning model named subspace KNN. KNN stands for K nearest neighbor. In the legend, there are 4 colored bubbles, one with blue color, the second with red color, third with yellow color, and the fourth with purple color. The bubbles actually show the correct prediction of a particular fault class, and the crosses shown on the scatter plot show the incorrect prediction of a particular fault class. So if you remember, we have prepared a total of 40 samples, 10 from each of the fault classes. So if we count the bubbles here, these are 10 in numbers: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It means that fault class 1 is perfectly predicted. Things will be more clear when we shall move to the second class, that is shown in red. If we count the bubbles, these are 80 numbers: 1, 2, 3, 4, 5, 6, 7, 8. It means 8 samples out of 10 are correctly predicted, whereas remaining 2 samples are incorrectly predicted. Further, the 2 crosses are of different color. One is of blue color and other is yellow color. It means that one sample of second fault category is misinterpreted as or incorrectly predicted as fault number 1, right? Why? Because blue color was assigned to fault class 1 only. Similarly, yellow color cross indicates that one of the sample from second fault category is incorrectly predicted as fault class 3rd, because yellow color was assigned to fault class 3. Similarly, if we move to fault class 3, there are only 5 bubbles, indicating that the correct prediction in this category is only 50% and incorrect is also 50%, from which 40% samples are incorrectly predicted as fault class 2nd because of red color, and one of them, one sample or 10% data, was incorrectly predicted as fault class 1. Finally, if we check for the 4th fault category, there are 8 purple bubbles, which indicates that the accuracy of prediction in this particular fault category is 80%, and it has got an inaccuracy of 20% with 10% inaccurate prediction of the 4th fault category, 10% as fault category 2 because of red color, and 10% as fault category 1 because of blue color. This result may also be interpreted with the help of this confusion matrix. The diagonal cells shown in green color show where the predicted class matches with the true class, and the pink cells show the incorrect classification or incorrect prediction. So rows show the true class and columns show the predicted class. So if we check for the fault category 1, you can see here the fault category 1 is having 100% entry in this cell. It means that the fault category 1 was perfectly predicted and it matches perfectly with the with its true class. That's why the efficiency is 100%, and it is evident from the scatter plots as well. So now if we check for the second category, the predicted class matches 80% with the true class. It means that 20% of this fault category must have been incorrectly predicted, and the details can be seen from these cells that 10% of the second class was incorrectly predicted as fault category 1 because of this blue cross, and remaining 10% was incorrectly predicted as fault class 3, right? Similarly, for third fault category, the correct prediction was 50%, incorrect was what? Again 50%, with 40% as fault class 2 and 10% as fault class 1. And finally, for fourth fault class, the correct prediction was only 80% and the incorrect was 20%, with 10% each from class 1 and class 2. These results are also summarized in the form of true positive rate and false negative rate. The true positive rate means the correct prediction, the rate of correct prediction, whereas false negative rate corresponds to the rate of false prediction. So fault class 1 was perfectly predicted, therefore its true positive rate is 100% and there is nothing in false negative rate. Similarly, for fault class 2nd, the true positive rate is 80% and false negative rate is 20, and similarly for third and fourth classes, which are 50-50 and 80-20 respectively. So if we try to find out the overall efficiency of this particular machine learning classifier, we can find out by adding these accuracies shown in the green cells, 100 plus 80 plus 50 plus 80 divided by 4, which comes out to be 77.5%. Also notice that as the efficiency or the accuracy of prediction goes on decreasing, the intensity of the green color also goes on decreasing. With 100%, the shade of green color was the darkest. With 80% and this 80% they are same, and the green color becomes a bit light when the accuracy gets reduced to 50%. Similar results are shown for the other classifiers. The KNN, the kernel naive Bayes classifier, is having efficiency of 85%. Fine tree gives an accuracy of 92.5%. Fine Gaussian SVM 95%. Medium KNN 97.5%. Again Gaussian naive Bayes 97.1%. Notice that the efficiency given by Gaussian naive Bayes classifier and medium KNN classifier is same, that is 97.5%. But if we notice another metric which is the training time. The training time in case of Gaussian naive classifier is 2.0579 second, whereas it was 3.4203 second for medium cannon. It means that although these two classifiers show same accuracy, but that as the training time for the Gaussian naive classifier is less, it means that it gives faster results and it is a better machine learning classifier in terms of speed. Another model named as linear discriminant shows an accuracy of 100%. That's why there are no crosses in the scatter plot and no pixels in the confusion matrix, and also no false negative rate. It seems a bit unrealistic because of the number of samples being selected for analysis. So we cannot guarantee 100% efficiency every time. So it may reduce with the number of with the increased number of samples as well as sample size. This table shows the results of all machine learning classifiers. The entries in blue color are those for which the scatter plot and confusion matrices are shown in the previous slides. One entry in green is corresponding to the highest efficiency model, but with the least training time. And the entries in red show the increased training time for the models with the same efficiency of 97.5%. Conclusions. From the present work using supervised domain of machine learning for fault classification, it is observed that the Gaussian naive-Bayes classifier gives highest accuracy of 97.5%. Linear discriminant classifier may result in 100% accuracy, but it may decrease with increase in sample size as well as number of data samples. Some classifiers provide the same accuracy, but the best model is the one which is having the least training time. As a future direction, similar analysis may be done with a higher sampling frequency of 48,000 Hz and with selection of different features to check for possible improvement in accuracy of fault classification. These are the references. So thank you all for listening patiently. The attendees may now post their questions in the chat box. Thank you.
Thank you, Mr. Atif Jamil, for your presentation. Ladies and gentlemen, the chat window is open now for live question and answer. The presenter will be available to answer your questions till the next session begins.